Integration using partial fraction decomposition. Objectives. By the end of this lesson, you should be able to recognize when to use partial fraction decomposition and apply partial fraction decomposition to the integrand to solve indefinite integrals. I want to start by thinking about the integral of a rational function. So if I have the integral of p of x over q of x, the answer can equal a combination of rational functions, arctangent functions, or logarithmic functions. Now, a rational function in general is a polynomial over a polynomial, and a rational function like this is considered proper if the degree of p of x, so the polynomial in the numerator, has a degree that's less than the degree of the polynomial in the denominator. So that brings us to what is partial fraction decomposition? So partial fraction decomposition, so we'll think decompose, is breaking down a proper rational function into the sum of two or more rational functions with simpler denominators. So let's take a look at an example of a proper rational function. I have x minus 1 divided by x squared plus x. So the degree of the numerator is 1. It's a linear polynomial, and then the degree of the denominator is 2. It's a quadratic. So since the degree on top is smaller than the bottom, this is a proper rational function. So that means we can break it down into two or more rational functions with simpler denominators. Simpler meaning that instead of being a quadratic, something nicer than a quadratic is a linear. So let's take a look at the exact rational function, the proper rational function we just saw. So x minus 1 over x squared plus x. That could be broken down into 2 divided by x plus 1, and then minus 1 over x, or we could think about this as plus negative 1 over x. So it's the sum of two rational functions, so 2 over x plus 1, 1 over x, those are rational functions, but they have nicer denominators. So x plus 1 by itself and x by itself is nicer than this quadratic x squared plus x. So the goal is going to be to take proper rational functions and decompose them, break them down, find their partial fraction decomposition, so that instead of integrating this on the left-hand side, we're going to integrate this on the right-hand side. So a partial fraction decomposition always exists for a proper rational function. And if the degree of the numerator is equal to or greater than the degree of the denominator, so not proper, we can still break things down, but we need to do long division first. So before we apply the method of partial fractions, I want to go over when to use the method of partial fractions to solve integrals. So sort of a strategy in general for solving the integral of a rational function. So if you're just given the integral of some polynomial over some polynomial, where do we start? So if possible, we want to simplify using algebra first. So if we can use some algebra first, and typically this is when the denominator is a monomial or just one term, then we can probably do a little bit of algebra and then not use any of the methods, just use the power rule for integrals. That would be the best possible scenario. If that doesn't work, if that doesn't apply, the next thing that we should try is u substitution, with u equal to the denominator of the rational function, or whatever that inside type of function is, if it's not just obviously the denominator. And if that doesn't work, if we can't apply u substitution, then we're going to determine if the integral is a version of the arctangent formula. So this may also need a u substitution depending on exactly what it looks like. And then finally, if that doesn't work, if the integrand is a proper rational function, we want to apply partial fraction decomposition. If the integrand is not a proper rational function, that's when we need to use long division and then apply partial fraction decomposition. So notice the method of partial fractions is last in this order that we would try to apply mentally as we look at the integrand and try to decide the best strategy to follow. Alright, let's look at this first example. I have the integral of dx divided by x squared minus 7x plus 10. So again, we'd first try u substitution, and that will not work. And then we try to recognize this as the arctangent formula, but that doesn't work either. So we're going to have to use this method of partial fractions. So I do have a proper rational function. The degree of the numerator is 0, because remember I just have a 1 up here, and the degree of the denominator is 2. So I can break this down. I can decompose this so that it is the sum of two rational functions with nicer denominators. And nicer meaning that instead of being a quadratic, each of the denominators is going to be linear. So how we're going to get those linear denominators is we're going to factor this quadratic. So this integral is the same as dx over the denominator factored is x minus 2, x minus 5. So x minus 2 and x minus 5 are going to be the denominators of their own separate fractions. So this integral is about to be the integral of one rational function with the denominator of x minus 2 plus another rational function with the denominator of x minus 5. Now the key is that we're going to need to find the numerators of each of these. Now what is true always, because we have linear terms on the bottom, because I have an x minus 2 in the denominator, what's always going to be above it is a constant, just a number. So we're going to indicate that number right now with a variable, and I'm going to call it a. And above this linear term, x minus 5 is going to be a different variable, and I'm going to call it b. So the whole goal here is we're going to try to find a and b. Now, that's going to require a bit of scratch work, and I'm going to do it off to the side. So let me just go ahead and draw this line here to indicate that this is going to be scratch work. Alright, so here's what I'm aiming for. What I need is for 1 over x minus 2 times x minus 5 to equal a over x minus 2 plus b over x minus 5. That's my goal. I need to find this a and this b. Well, on the right-hand side, if I want to force this to be one fraction, they would need common denominators. Well, the common denominator is just x minus 2 times x minus 5. So I'm going to have to multiply this right side on the top and bottom by x minus 5. So here's what I'm going to have. I'm going to have a times x minus 5, which is really just cross multiplying. So a is going to have to be multiplied by x minus 5, and then plus b is going to have to be multiplied by x minus 2, because we'd multiply the top and bottom by x minus 2 to get common denominators. And then all over my common denominator, x minus 2 times x minus 5. So now, again, I'm trying to force these two things to be equal. So what I'm going to do is I'm going to drop down the 1 over x minus 2 times x minus 5. So I can see that if I want these two fractions to be equal, well, their denominators are already equal to each other, x minus 2 times x minus 5. So what I really only need to be concerned with at this point is the numerators. So I'm just going to ignore the denominators now, and I'm going to focus on this line. 1 has to equal a times x minus 5 plus b times x minus 2. So that's what I'm going to focus on right now. I'm going to go ahead and just box that in to indicate that's what I'm working on. So I need to find a and b. Alright, so to do that, here's what I'm going to do. The first thing I'm going to do is I'm going to go ahead and let x equal 5. So if I let x equal 5, that's going to force this a term to disappear completely. So we'll show that work. That would imply that 1 has to equal a times 5 minus 5 plus b times 5 minus 2. So again, 5 minus 5 is 0, so 0 times a is 0. So what I'm left with is 1 equals 3b. So 5 minus 2 is 3, so 1 equals 3b. So in other words, b equals 1/3. So now I found my value for b that I can go ahead and substitute into this b up here. So we'll hold off on that because I also need to find a. And to find a, I'm going to go ahead and let x equal 2 because that's going to get rid of my b term. So if I let x equal 2, I'm left with 1 equals a times 2 minus 5, and then plus b times 2 minus 2, so that allows my b term to disappear. So I get 1 equals negative 3a. So in other words, a is negative 1/3. So a is negative 1/3, b is positive 1/3. We're going to take those and plug them back in over here. So what I'm about to have is a equals the integral of, so I have to just make sure that the a value, again, corresponded to the x minus 2. So negative 1/3 does have to go above x minus 2. And then plus above x minus 5 has to go my positive 1/3. And what makes this nice is that now, well, this is two separate integrals, so here's what I'm going to do as well. I'm just going to go ahead and put an integral sign right here and throw in a dx. So since these were added, I can split this up. So now this 1/3 can be brought to the front, or this negative 1/3. So this is negative 1/3, the integral of 1 over x minus 2 dx. Now we're going to do so many of these problems that it's going to be easy to see or recognize that the answer here is the natural log function. So this would technically be a u substitution. I would let u equal x minus 2, then du is dx, so this is 1 over u, and the integral of 1 over u is natural log. But because we do so many of these, I'm going to jump straight to 1/3 the natural log of the absolute value of x minus 2. So that's the answer to the first integral. And now this second integral, I can pull out the 1/3, and I'm going to get 1 over x minus 5 dx. So again, the u substitution that we would perform, letting u be the denominator, would give us just dx. So I end up with 1/3 the natural log of x minus 5 in absolute value bars. Indefinite integral needs a plus c. So this is my final answer. Alright, so partial fraction decomposition. Again, we had a proper rational function. We needed to factor the denominator to find my two linear terms. And then we just need to find the numerator of each linear term so that we can create those two separate rational functions. And that involves this process off to the right, which again is our scratch work, needs to be written separate. So that our string of equalities over here actually makes sense. So we don't want to do this work within the actual integral problem. Notice over here off to the right, there was no integrals. This is actually just a pre-cal topic. So if you did learn it last year, there is a separate way to do this using systems of equations, but this method is a little bit faster. But if you prefer the system of equations method and you have that from a previous class, then feel free to use that as well, as long as you can find those missing values of a and b to be able to solve the integral. And again, the integral of each of the rational functions should always be a version of the natural log function. So these ones ended up being nice because the denominator is just 1 x minus 2. We may have to actually perform that u substitution where we might actually get another value or a constant in the front out if this isn't just x minus 2. So for example, if it was 2x minus 2, I'd have to bring a 1/2 to the front as well. Alright, let's look at this next example. I have the integral of 5x minus 1 divided by x squared minus 2x minus 15. So again, we would try to use u substitution, letting u be the denominator. So then the derivative would be 2x minus 2. But notice the numerator is 5x minus 1, so u substitution doesn't work. So I have to use partial fraction decomposition. So I'm going to have to factor that denominator, so 5x minus 1. Over, if I factor the denominator, I'm going to get x minus 5 and then x plus 3 as my factor denominator dx. So now this is going to become the integral of sum a that we're searching for over x minus 5 plus sum b that we're searching for over x plus 3. So as long as the denominator factors to two linear functions above each linear function. So x minus 5 is always just a constant. And then above x plus 3, a linear function, is just a constant. So we need to find a and b. So we'll go ahead and do our scratch work again off to the side. Now what we want is 5x minus 1 over x minus 5, x plus 3, to equal a over x minus 5 plus b over x plus 3. And it doesn't matter if we put the variable a over x plus 3 or the variable b over x minus 5. As long as we keep that straight when we get to the end of the problem, the order that you put the a and the b, the constants over the linear terms, doesn't matter. So now what we're going to do is we're going to cross multiply. So what we're going to have is a times x plus 3 plus b times x minus 5. And so technically this would be all over x minus 5 times x plus 3. But remember, we're really just ultimately trying to set the numerators equal to each other. So the numerator over here is 5x minus 1. So now this is the equation that we're working with. So I will just star it this time, that this is what we're looking at. So what we're going to need to do is solve for a and b. So we're going to cleverly choose the x to get rid of a first, and then we'll choose the x to get rid of b. So the x value that would get rid of a, or make this whole term a 0, is negative 3. So if x equals negative 3, well, now what's different from the last problem is I have an x on the left-hand side. So on this left-hand side, I'm going to have 5 times negative 3 minus 1 equals, so now this is 0, so I'm just not going to write it, right? So negative 3 plus 3 is 0, times a is 0, and I am going to have my b stick around and become b times negative 3 minus 5. So now over here, this is going to be negative 15 minus 1, and over here this is going to be negative 8b. So I have negative 16 equals negative 8b. So b is now 2. And so now to solve for a, let's go ahead and let x equal positive 5, so I can get rid of my b term this time. So now I have 5 times 5, because I'm plugging it in over here on the left, minus 1 equals, and now my a is what's going to stick around. So I'm going to have a times 5 plus 3. So on the left I have 25 minus 1, so I have 24 equals 8a. So a is positive 3. So we take those values of a and b and then make sure they stay above the proper linear term. So a was above x minus 5. Over here a was above x minus 5. So over here what I'm going to have is 3 over x minus 5, and then plus b was 2, so 2 over x plus 3 dx. And so now the 3 and the 2 are just constants, so they're going to be in front of each of their own natural log functions. So in other words, this left part is going to become 3, the natural log of x minus 5, plus, and then this right part, when I integrate this, the 2 is going to be the constant in front, the natural log of x plus 3, and then plus c. So now the sum of these two natural log functions is my answer. Alright, looking at this next one, I have the integral of 4x over 2x squared minus x minus 3. So if we tried u substitution here, if we let u be the denominator, the derivative is 4x minus 1. So in the numerator, since we only have a 4x, this is not a candidate for u substitution. So I have to use the method of partial fractions. We'll jump straight to factoring the denominator. So I have 4x over the bottom factors to 2x minus 3 times x plus 1 dx. So now 2x minus 3 is going to be the denominator of one rational function, so 2x minus 3. And since this is a linear function, above it goes a constant a, plus x plus 1 on the other rational function, and because it's linear, a b goes above x plus 1 dx. So now we're in search of a and b. So again, let's go ahead and do our scratch work. What we need is for 4x over 2x minus 3 times x plus 1, we need that to equal a over 2x minus 3 plus b over x plus 1. So we're going to cross multiply to get that numerator that we need. So we need a times x plus 1 plus b times 2x minus 3 to equal the numerator on the left, 4x. And so again, we're only concerned with the numerator, so this is the equation that we're now focusing on. And we need to substitute in those values that will get rid of a and b individually. So we're going to need to first substitute in -1. So on the left, I'm going to have 4 times -1, so I'm going to have -4 equals, so this whole portion will go away, my a's. And now if I plug in a -1, I'm going to get b, so 2 times -1 minus 3. So this is -2 minus 3, so -5b has to equal -4. So dividing by -5, I'm going to get b equals positive 4/5. And then I need to substitute in a value that is going to get rid of my b term. So now I'm going to need to use a fraction. So the fraction that I'm going to need to use is 3/2. So if I go ahead and plug a 3/2 in right here, I'm going to get a 3 over 2, the 2's will cancel, and then 3 minus 3 is 0. So I'm going to have to let x equal 3 over 2. So if I plug in x right here into this 4x, so I'm going to have 4 times 3 over 2 equals, and so now I'm plugging 3 over 2 into this a, so I'm going to get a times 3 over 2 plus 1. So on this left side, this is 12 over 2, which is positive 6. And over here, 1, that's 2 over 2, so this is 5/2. So this is 5/2 a. So now, to get a by itself, we have to multiply both sides by its reciprocal, 2/5. So what I have over here is 12/5 for a. So a is 12/5 and b is 4/5. So I'm going to take that and carry it back into this decomposition. So this is the integral. So a was 12 over 5, and then times 2x minus 3, or over 2x minus 3, plus 4 over 5 over x plus 1 dx. Alright, so this one is going to be slightly different because I'm going to go ahead and pull out the 12 over 5. This is the integral of dx over 2x minus 3. And then I'll split this one up too. This is 4 over 5, the integral of dx over x plus 1. So here, we're still going to get out natural log, but when I perform my u substitution, so u would be 2x minus 3, so du is 2 dx, and all I need is a dx, so half du equals dx. I'm going to have to put a 1/2 in front. So in front, where the 12 over 5 already lives, I'm going to have to put a 1/2. So I'm going to get 12 over 5 times 1 over 2, the natural log. Whoops, that looks a little weird. Looks like ln, it's just ln. So natural log of 2x minus 3. And then plus, well, this is just x plus 1. There's only a 1 in front of the x. So this is just 4/5 natural log of absolute value of x plus 1 plus c. So now here I can reduce, I can cancel the 2 up here, so I'd get 6 over 5. So we have 6 over 5, the natural log of 2x minus 3 in absolute values, plus 4/5, the natural log of x plus 1 plus c. So this is my final answer. So it works the same way, but my u substitution would give me a constant in front other than 1. I'd have to account for the 1/2 that would come out of taking the derivative of 2x minus 3 and dividing the 2 on the other side. So when the linear term on the bottom has a leading coefficient of 1, I don't have to worry about it. When I have any other leading coefficient, it's going to be 1 over that leading coefficient that's going to come to the front. Alright, so now I want to go over two problems that do not require partial fraction decomposition, but now that we have it, you might try to jump straight to it when it doesn't apply. So here I have 1 over x squared plus 4 dx, which is an arctangent problem. So the solution is arctangent. And one of the best ways we can recognize we cannot use partial fraction decomposition is that this denominator does not factor. So this is the sum of squares, not the difference of squares. So the difference of squares can factor if this was x squared minus 4, but as it currently stands, it is not factorable. So we have to recognize this as 1 over x squared plus 2 squared dx, which is the arctangent formula. So this is my a. So we have 1 over a, and then arctangent x over a. So a is 2. So this is just 1/2 arctan of x over 2 plus c. So this is my answer. But again, it is a proper rational function. So our answers to rational functions being in the integrand are combinations, remember, of rational functions, logarithmic functions, and arctangent functions. So here's an example of one where it is not a partial fraction decomposition. And then here I have a rational function. This is not a proper rational function, but it does have a monomial in the bottom, meaning that we can split it up to solve. So I can think about this as, just to show the intermediate steps, this is x cubed over x squared plus 1 over x squared dx, meaning this is the same as the integral of x plus x to the negative 2 dx, which requires no special methods at all. It's just the power rule for integrals. So it would be x squared over 2, and then here I'd get x to the negative 1 over negative 1, right, plus c. So we'll just leave it like that. We won't bother simplifying that. But just to show that when I have a rational function, now there's just so many strategies. So we jump straight to the first strategy here. If I can use algebra to avoid any of the other rules, I should. So when there's a monomial, just one term on the bottom, I should try to split it up if possible. Alright, so let's move on to the last problem, which is going to be a bit of a long one. So I have the integral of x cubed plus 1 over x squared minus 4 dx. And let's try to go through this one using the strategies, as though we don't know the method to approach it. So as I start, I want to see, can I use any algebra first? Well, there's not a monomial on the bottom, so I can't split this thing up. And maybe you would recognize, well, the bottom would factor pretty nicely, but it's not going to factor and cancel with anything in the numerator, so algebra won't work. Moving on to u substitution, if I let u equal x squared minus 4, the derivative is 2x, and in the denominator I have x cubed plus 1, so that's not going to work either. This is not a version of an arctangent formula, so I would think to use partial fraction decomposition, but this is not a proper rational function. So the degree of the numerator is 3, and the degree of the denominator is 2, so the top is bigger than the bottom, so it's not set up as it currently stands for partial fraction decomposition. So I have to use long division to rewrite it so that it is proper. So way over here off to the right, I'm going to go ahead and do my long division. I'm dividing x squared minus 4. So remember, just division, we divide the denominator into the numerator, so x cubed plus 1. To remind you about long division, so we're looking for, what do I have to multiply x squared by to get to x cubed? So I have to multiply by x. And then I multiply x times this divisor. And so x times x squared is x cubed, and x times minus 4 is minus 4x. And then with division, we subtract this quantity. So in other words, this is going to become plus negative x cubed, and then plus 4x. So as I add down, the x cubed and the x cubed cancel, give me 0. 4x stays 4x, nothing cancels with 4x, and nothing cancels with positive 1. Alright, so now I can't force x squared to go into 4x plus 1. So this is my remainder, 4x plus 1, and the way that we write remainders when we divide polynomials like this is that this is x plus the remainder, 4x plus 1, over the divisor, x squared minus 4. So, going back to the problem, what I did was I rewrote x cubed plus 1 over x squared minus 4 as this whole quantity. So, x plus 4x plus 1 over x squared minus 4 dx. So now, this portion here, x, is clearly easy to integrate. So as its own problem, we just apply the power rule. But now this part is set up for a partial fraction decomposition. So now I have to do my scratch work. So in other words, here's what we're aiming for. This is going to end up as x plus the bottom of this factors to x plus 2, x minus 2, so we're going to get a over x minus 2 plus b over x plus 2 dx. So we need to solve for that a and b. So now we're going to have more scratch work, right? So this was the scratch work for the long division. We're going to try to cram the scratch work in for solving this portion here. So we're trying to force 4x minus 1 over x squared minus 4 to equal a over x minus 2 plus b over x plus 2. So we're going to cross multiply as we have in the previous problem, so that 4x minus 1 has to equal a times x plus 2 plus b times x minus 2. And then we go ahead and let x equal plus 2 and minus 2. So if I plug in minus 2 first, I'll get 4 times negative 2, not minus 2, equals, so the a terms will go away, and then I get b times negative 2 minus 2. So here I get negative 8 minus 1, so negative 9, equals negative 4b. So b is positive 9/4. And then if we let x equal positive 2 this time, we'll get 4 times 2 minus 1 equals, if I plug in positive 2, my a will stay. It'll be 4a. So this left side is now 8 minus 1, so 7 equals 4a. So a is 7/4. So let's take that back to the original problem. We are really integrating x plus a is 7 over 4 over x minus 2. B is 9 over 4 over x plus 2 dx. And now we can integrate each piece. So the first part by the power rule is x squared over 2 plus, now this is 7/4, the natural log of x minus 2, plus 9/4, the natural log of x plus 2, plus c. So now, whoops, this is my final answer. So again, it's going through that process mentally. This is why integrals are harder to solve than derivatives, because there are no set rules, and we just have so many different strategies depending on what the integrand looks like. So for rational functions, our options are algebra first, use substitution, apply the arctangent formula, or use long division and or partial fraction decomposition. When I have a product, I can try use substitution, or we have integration by part. So there are just all these different methods that we have to try to mentally think about first, so that we don't go through and waste a bunch of time trying different methods that are just going to lead us to nowhere. So it's really getting practice, just like with sequences and series, and figuring out what does this look like, so what strategy do I have to apply.